So there are a few optimizations that you can actually do to speed up things when dealing with linked lists, and they will save you a lot. They will save you a couple of cycles, which you might want to do if you if this is an operation that you're doing a lot, and yeah, if you already have some pointers in your system. So you can call the internal list functions, which are preceded by the underscore underscore. And right, I mean, when I talked about, if you look at, for example, here, this is the internal implementation. So it takes, and this is what you call. So you either can call it list delete, for example, with the list head and an entry, or you can basically go to in this direction, where you basically have the underscore underscore and then have sorry, this one, and have both the previous and the next struct not struct pointers already in your code. So if you can call this will save you basically if you dereferencing cycles basically. um, well, one thing also that I would like to note is that when we were talking about linked list manipulation here, you see that we are only dealing with the list head struct that you have added to your code. So the whole thing is completely oblivious to whatever things you're running in that struct basically. Okay, so this is an optimization that is not really worth a lot of work for most kernel developers. You can just use the list delete or the list add as is. So how do you traverse a linked list? The first way is basically using list for each, and that basically iterates over the whole list. And your code in this case will be you'll define the list head pointer, and you'll basically iterate from p through fox list, which is your list basically. But p will be pointing basically to the entry in the list, in the head list. So p in this case, so if you look at this at the definition of the function definition, it actually tells you that this will basically point you to the head of your list. It's which is not a lot useful, because it will just tell you how to jump between the lists. It's not really pointing you towards the data in your list, because in your linked list in your element, because as we said, you have a node in your linked list, and that node has the struct that is like list head, the list head struct, and you're basically jumping on the list head structs. You're completely unaware of where the actual node is. So that you do if you're just trying to basically know, well, maybe the memory address, where does the where is the memory allocated to each element, for example. But we talked about the list entry function that can basically give you, if you remember the members, I mean, given it can give you the output, the member variable of the linked list. And well, you can use that coupled with list for each to actually get the data that you need. Okay, so that is basically one of the most useful things that you have for this entry, because then you can return the parent structure containing the list head basically. So since list entry since list entry list for each basically gives you the list the list head address, and container of, and hence list entry will give you the parent structure as I discussed a few minutes ago. Then you can actually use that to get the address to the parent structure. So now we are back to the Fox structure instead of just pointing to the list head list that we had in the Fox structure. So this would be a way to actually get your data to traverse the linked list. But the third way, which is used, is that you have basically a function that is already implemented for you that's called list for each entry, and then you will have your basically f will be pointing to your to the data that you need, to the parent of list head basically. And yeah, so you can use this list for each entry instead of using these two lines basically. Okay, so it's a combination of both of them, you can say. And this is the implementation, and list for each entry, it comes in different flavors. So you have list for each entry continue, list for each entry reverse, list for each entry without anything, list for each entry continue reverse, and each one of them basically traverses the linked list in a different way that you might want to take a look at if you want. Then if you want to remove as you iterate, then there's actually a function that is called list for each entry save, and use this version in the same manner as list for each entry, except that you provide also the next pointer, which is of the same type as pos. So the next pointer is used basically to store the next entry in the list, making it safe to remove the current entry. So that's what you use when you're traversing linked list while actually wanting to remove the elements at the same time. Because otherwise, if you remove the element by basically, or maybe even change the data in the element, change the pointers in the element, you might end up with a broken linked list. So the way to do that is just to basically use list for each entry save and know your entrance points and know what is the next pointer that you need to point to.